Welcome, everyone, to our monthly Science of Alt Protein seminar. My name is Amy Huang, and I'm the Associate Director of Scientific Ecosystems at the Good Food Institute. For those of you who are here for the first time, welcome to our community. The Good Food Institute is a nonprofit think tank. We're 100% driven by philanthropy, and our goal is to build a world where alternative proteins are no longer alternative. If you're looking to take a deep dive into the science of plant-based fermentation or cultivated meat technologies, check out our open access resources at gfi.org/science. We have so many new technical publications that have gone live in recent months that I think will be really useful to the community. And with that, it's my pleasure to introduce Dr. Volker Lammers. He's a food engineer with a focus on the development and implementation of innovative technologies for the sustainable production of high-quality foods. He studied food technology and biotechnology at TU Munich and completed his master's course in 2011. And then between 2012 and 2016, Volker worked as a research assistant at ETH Zurich, where he received his PhD at the Laboratory of Food Process Engineering. In 2016, he joined the German Institute of Food Technologies and currently leads their process engineering department. That group focuses on industry-ready solutions in the field of extrusion, 3D printing, and other major texturization technologies for plant proteins. So in today's seminar, Dr. Lammers will get into that research a bit more, share robust and scalable extruder solutions that offer high throughput rates for plant-based meat production. And he'll also describe industrial scale post-extrusion methods, including cutting, shaping, and marinating. So with that, Dr. Volker Lammers, welcome to our seminar. Please feel free to start sharing your screen, and we look forward to your presentation.
Thank you, Amy, for this very kind introduction, and to GFI for having me. It's a pleasure to present today and to give you some insights from our work we do here at the German Institute of Food Technologies. Today I will report a little bit about scalable technologies for protein texturization. But before we start, I would like to give you a brief overview from where we are coming and where we are located. So here you see a map from Europe with Germany, and we are located at one spot, but I would like to take you a guess basically what this map of Germany represents. So you see here many green dots and some yellow and red dots on the map. So the green ones, so this map actually represents the livestock density in Germany. So green areas with low density and red ones with very high density. So, and now you could take a guess. So where the dill is located, so it's actually really in the center here. So I don't know if that was a reason in the 1980s when the Institute was founded, but one of our missions is to collaborate with people from the agricultural area, from the food industry, and also from food processors and retailers. We consider ourselves as a knowledge provider and as a bridge between the academic world and the food industry. So with this, I would like to give a brief overview of our organization. So the DIL e.V., German Institute of Food Technologies, is a private research institute with about 200 employees, and it is structured into three sub units. So it's the non-for-profit institute with two subsections focusing on DIL technology and DIL engineering, which are two commercial entities looking for collaborations with partners from the food industry. Beyond that, we offer here at DIL also a studying program entitled Food Process and Product Engineering in collaboration with the Veterinarian University of Hanover. It's a new studying program introduced 2 years ago for specific food technologies. Beyond that, we have many startups and small companies located here at our campus. Most of them are spin-offs from the DIL. And beyond that, we have also some strong networks with local ones, LE Food, EIT Food, but also many connections with GFI, not mentioned here in particular. And we call it here also on the bottom right, the factory village, where we have some strategic partners, particularly collaborating with them in the field of protein texturization and in the alt meat space, naming here Bühler, Air Liquide, ThyssenKrupp, for example. The DIL is a registered association, means we have members, and the members are our best references. So we have about 190 member companies on our board. So from startup, small companies up to very large companies from the ingredient, food industry, feed industry, and machine building industry. So from very different spaces. And our mission is also to bring everyone together and to connect with each other to bring the food system forward. But with that, now I go into the presentation for today. What you see here is an overview from a publication from Birgit Deckers. She also had a GFI talk, I think 2 years ago, about structuring techniques. And this overview I like to start with because it gives a good overview what technologies are available today for structuring proteins. And you see here in the field commercial availability. Some are still under research, some others are already widely established. And there are many interesting new research fields popping up and new technologies developing, but we're focusing today here on extrusion. And that's for some good reasons. First of all, it's commercially available. We create different types of structures from various selection of raw materials, and it's a scalable technology. So extruders can be found in different sizes, and capacity, scalability, and process robustness are key parameters when it comes to the commercial viability of processes and products at the end, particularly when we consider price parity of alternative meat products compared to the meat counterparts. It's quite a pressure to develop or to produce good products for affordable prices. So basically, when we talk about protein texturization, we differentiate between low moisture extrusion and high moisture extrusion. Also known maybe the low moisture extrusion as dry tex or texturized vegetable proteins, TVP, and the high moisture extrusion. And there are also different names around like HMMA and or wet texturization. But today the focus will be more on the HME product, but to explain both. So the low moisture extrudates, they are characterized by an expanded structure. They have a long shelf life because the water content is so low that they are shelf stable. And those products are mainly used for burgers, minced meat, sausages, and other types of meat analogues. So they need a rehydration step, if you see here the extrudates and binders, to make a burger patty or to make a sausage. On the right, you see the example for a high moisture meat analog, and it's characterized by the wet structure or wet product. One drawback might be it needs to be chilled or frozen because we need to ensure that it has a long shelf life and we have a safe food product. But there are few advantages. It resembles more muscle meat, for example, chicken, beef, or pork meat, and can be used for whole cuts. And after the extrusion process, the product is, let's say, almost ready to eat. We don't need any additives or numbers or complex formulations. That is an advantage. And I will present some high throughput solutions today. So that will be the focus of the following presentation. What's the structuring method of the high moisture extrusion process? Here you see a schematic of the extruder. The extruder is composed of a motor, of a gearbox, of an extruder barrel, and in this extruder barrel there are sitting two extruder screws, typically co-rotating intermeshing twin screws. And in this twin screw we mix a protein powder typically with water, and we create a type of a dough in the extruder barrel. By the friction of um, of the screws and the heating of the extruder barrel, we create a mixture of the protein water, and this mixture it's heated up to more than 100 centigrades, and subsequently cooling in the cooling die creates a typical fiber profile that looks similar to meat products. How is this structuring happen in detail? So we have the extrusion process where the ingredients are mixed with each other, heated, sheared, and that happening in the extruder part. That is the hot part in simple words. And on the right, or attached to the extruder, we have the cooling die, which is simply said a flow channel, or also considered as a heat exchanger, where we remove the heat from the material, and by the subsequent cooling of the material, we have some structural changes of the material. From the protein melt, it cools down, and we have a laminar flow profile in the cooling die, and this profile is somehow fixed, and fibers are created. Here you see an image of an extruder, how it is used at our institute. It's a production scale extruder from a Bühler company, and the process looks like we have here on the top a powder feeder. The powder, the protein is conveyed into a preconditioner, mixed here with water in the extruder barrel, and then at the end plate, not indicated here, we have a cooling die. So the entire process is controlled by a control panel and almost fully automated system. So this is where the product flows. And at the end, I said there are the cooling dies, and the capacity or the scalability of that extrusion process also depends very much on the design of the cooling dies. So you see here a selection of dies that are available in our pilot plant. You see there are different geometries, from slit cooling dies with a rectangular design or annular design. Different in diameter, they are different in the length, and it's a science on its own. What's the best design for a cooling die? Because you can imagine the design and the operation mode plays a huge role on the structure formation afterwards. So here in summary, we offer solutions from 100 kilogram to 1 ton metric ton per hour, which is, to our knowledge, the state of the art today, and makes the product, or it's a contribution to make meat analogues also more affordable. I share with you a video how we do it here at our institute. It's a short overview, not showing all opportunities we have, but I think it gives a good overview. Starting from mixing and feeding the ingredients into the extruder. Here you see the cooling die outlet where the so-called, yeah, we could call it slab, carpet, or we have different words for it, before it enters a size reduction cutting machine, and some chunks or are produced. And to make them shelf stable, we freeze them in a drum freezer. So that's a simple way to produce these type of products, and these can be used as chicken analogues, for example, and being packed. But this was now a very simple process, so to say. But starting and looking at the extrudate that's coming out of the extruder, we have a product that is moist, dense, and the fiber structure we may not see directly at the beginning, but it's more inside. And so the big question we have is, how can we make a tasty alternative to meat from that high moisture extruded proteins? And here I will give you some examples on the research we are doing and applications, and yeah, give you an overview. So first of all, when we work with different ingredients, we will achieve different types of structures. So we work with soy proteins, pea proteins, wheat, gluten, fava bean, also with some more exotic ingredients like insect protein or algae, and other single cell proteins. And depending on the ingredient, you see you get different structures, but also different colors. And that is very important when we consider the consumer acceptance also at the end. So taste plays a role. When we work with fava beans or peas, we may have some off flavors and a beanie flavor. The appearance plays a role. Dark brownish color is not what works for all kind of meat alternatives. And the shape, how we make final products out of it, is also very important and not to be underestimated. Texture and mouthfeel are key parameters. So the experience when we eat the product makes is a very critical quality parameter, and also how the products perform in the pan when they are fried, when they are cooked. They should have a good performance. And last but not least, the nutritional profile should also be considered, because when we work with plant proteins, we may have deviations, or we surely have deviations in the energy density and also on the macro and micronutrients. So with that having in mind, I will go a little bit further. Yeah, here are some more of the ingredients I just mentioned. That is the selection we are working with here, and probably there are also many more to be tested. We are always on searching, seeking for the best functional protein to be used in extrusion. But now what's important, I've shown the video on the texturization in the extruder. Mentioned we have different solutions, different cooling dyes to create or to produce, let's say, up to 1 metric ton per hour. But what is also important and not to be underestimated is, what are we doing afterwards? So we have the raw material handling and the extruder, then the cooling die for the structure formation, but then also parameters like size reduction, marinating, freezing, packaging, and also maybe other combinations play a role to really create food that is tasty, affordable, Yeah, so that's the challenge. Here you see an example of a classical texturate on the left. And yeah, how can we pull it? How can we make this structure visible? The easiest way is to do it by hands, pulling it apart. Then you see the nicely formatted fibers. And you can make very good products out of it, but obviously pulling or shredding by hand is not the way to go. It's not economically viable, so we need different ways to do that. We also need to keep in mind not every slab or carpet coming out of the extruder has the same geometry or size. So all subsequent processes need to be somehow adjusted or tuned to make a good product out of it. What you see here is the exit of an endless strand coming out of the cooling die. What we have developed to make it a little bit easier is we have this axial cutting unit, so where you can attach this feature here on the right to the exit of the cooling die, and then it is cut in the axial flow direction. Our engineering workshop, we can create different designs and patterns, something that looks like more like a chicken chunk, or if it's more going in the spaghetti way, you could more resemble minced meat or stripes and others. And what you don't see here is we have also a radial cutting unit. It means that you also have a rotary pelletizer cutter at the end to make to design to cut to the right length of the product. But also you could use other size reduction machines. Here, for example, that is a, a cutter from the company Holak, which is can be used to make different types of shreds, cubes, and stripes. It also has a very high capacity. That is important to look the capacity of the downstream equipment. It's operated in a semi-continuous mode, and we have here different grids, knives available to create different structures. Another way to do it, and the meat industry knows it very well, are the meat grinders. So if we have, after cutting, for example, very straight and sharp edges, we want to make the product look more naturally. And then this meat grinder may help to make it look more natural, because then the edges are a little bit more grounded. And we could also mix it with other ingredients already to add marinade or other components. So just summarizing up the steps: cutting and size reduction, some general considerations. There are many different machines available. All have pros and cons in using. Some work better for strips, some others more for pulled type products. But we need to consider the formulation of the product, the cutting temperature. I didn't mention that so far. It's an important factor because when the product is fresh, means warm or chilled or thawed, we have different cutting performance. We recommend to cut the product when it's still warm, because then the material is a little bit more elastic and we have better flexibility to cut the product. And where we need to consider the targeted size and shape. And one thing to be considered is, on the one hand, when we make a very natural type of cut, we may create also many fines, small pieces that cannot be used for the real product. And sometimes it's a little bit a trade-off to find the best cutting setting, let's say. That is the work the food technologist has to do while developing such products. And a rework of the finds or of the rejected products is to be considered to reduce the waste of the product. When we consider the product is now extruded and cut, it may still have not the best taste, it may have a bland taste. We can, of course, add ingredients, spices, salt, pepper, or others into the extruder, but maybe we also want to add a nice marinade to have a very specific type of product. And here we can use these kind of trolley tumblers, which we have here in our house, having a batch size of several kilograms, and we have a gentle mixing step where we can mix the cut extrudate with spices, herbs, and oil and other ingredients. And it's very easy to integrate it into the processing line. General considerations here for tumbling and marinating. To avoid a flat bland taste, marination and addition of spices after extrusion is a good choice, probably. And if we add it before we freeze or pasteurize or pack the products, we have also more security about the food safety, because the more ingredients we add, and when it's a warm environment, microbes and bacteria may grow. So this is something to be definitely considered. And the HME products, they absorb the marinades better when it's fresh and warm, but also to be known that further conveying or handling of the material may be disturbed when we have too much marinade. Freezing is a potential way to stabilize the product, as mentioned and shown in the video before. Here at Dill, we do it with the so-called zip roll freezer, where a food product enters a drum freezer, and the drum is chilled or cooled by liquid nitrogen to about minus 70 centigrade, so really cold. But it has the advantage that we can cool down and freeze the product at minimal space that is required. And we create this IQF quality, which stands for individually quick frozen. So afterwards, when we have the material packed, we can also handle the chunks or strips individually. And we can operate at very high capacity, which is also important to have a scalable process. Besides the drum freezer, we could also use belt freezing systems. Here we see how someone is putting strips to the belt, but it's also suitable not just for the larger strips, but also for smaller pieces. When we develop products, we also often do that in collaboration with our butchers from the meat technology lab. So here you see the meat lab with a cooker here on the right, a tumbler, vacuum filler for sausages, a meat grinder here in the back, smoking chambers, salt injection machines, so everything that is used in the meat industry day by day. And it's very helpful to use this equipment for prototyping and developing meat analogues, and also having in mind when these type of products shall be once produced, and some of the customers or applicants may come from the meat industry, then it has the advantage that it's equipment they already know. and which make many things more easy when it's working on those machines. So to sum up a little bit, scaling the high moisture extrusion process, we have here this extrudate slab I showed at the beginning, and I asked, or there was the topic, how to create a tasty product out of it. We have on the one hand the process technology, and one key message is that all the processes downstream the extruder need to match with the extruder output. It doesn't help when we scale the extruder or the cooling die to 2 or 3 metric tons, but we don't know how to handle the output afterwards. But on the other hand, the extruder and the cooling die, they should have a match so that the cooling die is not the bottleneck of the entire process. So also not helpful to have a very huge extruder, but just a small cooling die, then it's not a good value for the investment of the extruder. Then we need to take an eye on the integration of the downstream equipment into the production line. So how can we make it in a smart way that we cut, marinate, or tumble the product, ideally in a continuous mode, because that saves some labor and reduces some errors also. And one thing not to be underestimated is the hygienic design of the entire production line, and to have a look at all microbiological matters and issues that can arise from a long shift production, because the high moisture extrudates, they are more susceptible to microbiological contamination than the dry TVP products. Okay, with that, I have a few product examples, starting here with some sausages and burger patties. Those are not 100% based on HME products, rather than on a mixture between the low moisture extrudates with high moisture extrudates. We've identified that this has some advantages when the low moisture extrudate can keep the water very well, and the high moisture extrudates gives a bit more bite or texture into the product. So there are many different opportunities to design or develop products. Here it is. Here you see a reference that was published on meat hybrid products. So of course, it would be nice if we can go fully plant-based, but in some cases, mixtures of meat and plant proteins may be considered for taste reasons. And here we did some investigations based with the high moisture extrudate and the low moisture extrudate coming from pea, sunflower, and pumpkin protein, and then it was mixed with different ratios in meat, beef products. And you see there are differences in the color, particularly here for pumpkin. It's getting a little bit greenish. Yeah, but it's also a good route to go and to develop new type of products. Some of our latest developments relate more to hole cuts, and that we develop products that are a little bit thicker in the product size. So just as a reference, the cooling dies I showed you at the beginning, they have height or gap width, if you wish, between, let's say, 10 and 15 millimeters. You can make them larger, you can make them smaller, but it will always affect the structure. We cannot go with the height to infinity, because then the entire structuring process will be disturbed and look a little bit different. So making larger pieces with a higher thickness requires some other engineering approaches, and we have found some ways to make larger pieces here. Also here in a product simply based on water, soy protein concentrate, oil, and a little bit of yeast extract for the taste mainly. But the goal is always how can we make the product just by physical or mechanical processes which are natural. And the goal is, I think, yeah, or what we've achieved here is that we have make the fibers visible. We have a product with a thickness larger than 20 millimeters. It also has an improved juiciness and better frying performance compared to yeah, products we have developed a couple of years ago. And we hope that we go further this way to scale it up. Here you see also a little bit of the structure. I don't know how it is with my timing. I'm almost finishing. So scanning electron microscopy images. Here on the left, the plant-based meat analog from soy, and on the right, meat-based reference. You see they are on the same length scale, the fibers that we can create. But we also know it doesn't tell you this image how the product tastes or how it actually look like. Scale. Before I close, just in something a little bit away from the typical high moisture extrusion, we have developed a 3D printing process. So 3D printing was many years in the news. Many research institutions and startups have worked or worked on it, but one matter was always the scalability of that process, particularly when you consider a cartridge system where you have a prepared material and you press it through the through a nozzle and you create a 3D printed object. We have designed a process based on a twin screw extrusion process where we add, similar to the high moisture extrusion process, the protein, mix it with water, and then we have here and that is more for measuring matters in inline capillary rheometry and it's slit die, and then at the end a printing head. And just the difference we are using is that the table we have here is moving in the Z direction, and we can create 3D objects with that. And we have additionally the advantage of the extruder that we can mix heat and shear in the process before we extrude, before we make the 3D printing object. So that was, yeah, almost a couple of years ago where we made the first objects. This is how it looks like. We have the extruder here in the back, and in the front the table moving. And those are products that can be produced. We have geometry freedom, we have high throughput, we have some structuring, we can create new product designs, but we also know this is not the end of the story because the structure is not what we want it to have. So when we look into a meat-like structure. So we don't have a visible fiber orientation in the 3D printed sample. It's more like a macro scaling on a macro scale. But we have good water binding and a homogeneous protein network. And let's see what can be done with that technology in the future. Before I close, our services that we offer, we support our partners from prototype to production, and we want to offer a route to market for R&D projects, and we start typically with the small scale extrusion at lab scale testing. Then it's always the question, does the product that was developed on small scale, is it transferable to industrial scale? And if yes, we may also do toll manufacturing to produce the products that can be actually sold on the market. And we also support in consulting when it comes to equipment sales or to establishment of own productions. That's an image of our pilot plant. And with that, I would like to invite you, every one of you, to the DIL Technology Day that happens in a couple of weeks in June 11 and 12 here in Quakenbrück, with also a live demo for extrusion involved. Good speakers, nice event, networking opportunities, and many more. So with that, I also like to thank my team for doing all the research and developments. Also, a big thank you to many academic partners, funding agencies, platforms, and industrial partners we are working with, and many more. And last but not least, thanks for your attention and for GFI for having me here today.
Thank you so much, Volker, for your presentation. I loved especially your slide on the fiber lengths of the extruded meat analogues in contrast with our conventional counterparts. That was a very, very nice visual. For those of you in the audience who have not yet gotten the chance to ask your questions, please do drop them into the Q&A section of your Zoom bar so that we can get through them in this next portion of the event. Thank you again, Volker, for a fantastic presentation. I'm going to start us off with a question here from an audience member about whether you can articulate the largest areas um, of research bottlenecks within the high moisture extrusion umbrella. What are some of the biggest bottlenecks or hurdles scientifically or technologically that we need to make progress on to make even better products?
There are different aspects. One aspect we're working on or considering a lot is both technologically and scientifically. What is the best raw material to start with? Because we believe extrusion is a principally simple process and scalable and robust. And we often get the question, yeah, but why are the products still so expensive? And then one thing is we have to answer is that the ingredients are also very expensive. The ingredients are often highly refined. We must say, if we work with isolates, pea protein isolate, which is a typical ingredient, it's not cheap, and if that already makes a huge fraction of the complete product, I think that is where we need to put more research in, how to find gentler ways to fractionate the ingredients, to source them, to make the entire process then more cost efficient. That is one thing from the ingredients part. Then one thing that we consider is how making the product more stable. What process control can we add to it that we don't have product or quality fluctuations, and also from an analytical point of view, standardizing the quality of the products, that it's not depending on the operator what is good or bad on a personal perception, but to have it more on a scientific basis. Yeah.
Thank you. That helps a lot. One follow-up question on the, you had mentioned kind of the ingredients being quite expensive. Along that line, an audience member is curious how you are viewing the role of methyl cellulose in this process. Is high moisture extrusion a good way of removing methyl cellulose from the production process, or are we still looking for a viable alternative?
Mhm. I think the issue or the matter of using methyl cellulose in many meat alternative products can be a driver to go more into the high moisture extrusion direction because as shown in the examples presented today, we typically use water, protein, maybe oil, maybe something to give it a little bit more taste, plus a marinade, but then that's it. And there are, yeah, also some companies that are using the high moisture extrusion process and that are very successful with that. We know also that, and that is, I think, clear plus for the high moisture extrusion process. For example, the sausage I've shown, it has methyl cellulose, honestly, yeah, because it also has a dry tex product, and we need to somehow glue it together. And we don't have also a better alternative in that field, but that's a little bit why we put our research into high moisture extrusion.
Thank you. At the start of the presentation, you also mentioned that high moisture extrusion doesn't require food additives, and as an advantageous, beneficial part of the process. Why is it that food additives don't as much need to be a part of the picture technologically?
Sorry, I missed the last part of the question.
Question is, why is that? When you mentioned that high moisture extrusion doesn't require food
Oh,
additives, can you comment on why that
yeah.
is?
Okay, because the structure formation takes place in the extruder and cooling die section, and I get this endless sheet out of the extruder, and I create already the fibers. And if I add oil and other spices, then I have almost everything I need for the recipe. And I don't need any methyl cellulose or something to glue anything together because I'm coming from a larger piece. And I can take the larger piece and make smaller strips, chunks, nuggets out of it, rather than the other way around for the TVP where I have small granules and I try to make a larger piece of it. If I want to go that way, I need to glue. Yeah.
Got it. Thank you. We have a question here around the fact that extrusion seems to more negatively impact nutrition and bioavailability of plant-based meat products due to thermal degradation. How does high moisture extrusion, or how might high moisture extrusion protect against nutrient degradation or improve this overall?
Nutrition questions are always exciting, and but I think it's a very difficult topic in general. So I would say the extruder is a machine used in food industry for a very long time. You can make a large section of or large variety of products in general, starting from pasta, flips, breakfast cereals, and many more. In my opinion, it matters more what ingredients I put in rather than the technology itself. So I have here a completely thermomechanical process. When I do cooking, when I use other machines, I may also have a similar impact. This is just more, it's more automated. Yeah, it is a continuous mode. It is high throughput. Yes, but I don't see really in over processing here. I think it's more when it has negative impression. It's more that we do not over processing, but in many foods over formulating things. That is my opinion on that. Yeah.
Gotcha. Are you aware of any efforts to make advancements to extrusion or high moisture extrusion such that we are protecting more kind of proteins, nutrition from biodegradation?
Mhm. I mean, sure, we do our research in that field, so do many other research institutions and universities. Uh, though extrusion is existing for a longer time, I think there is still so much potential to be explored that we haven't seen so far. So I think there are many options to improve also from a nutritional perspective the products. And but of course, there might also plop up new other technologies outside the field of extrusion. If we look in all the fermentation stuff, cell cultivation, and there are many others that are also interesting. And maybe we can bring them at one point together to make something really new or disruptive when bringing things together.
That is a great segue into this next set of questions around, um, on one hand, cultivated meat and plant protein hybrids, on the other hand, um, relating this process to microprotein and fiber structure enhancement of microproteins. Have you explored the intersections of these technologies with other kind of fundamental production platforms beyond plant plant-based meat? And if so, what are some of the major areas of extensibility or collaboration that you see?
Mhm. I mean, the standard sources of materials I've shown, it's mainly and still the plant proteins, and we look how can we produce the proteins maybe in a more efficient, gentler way. But we have also worked with microproteins, with mixtures, or with new ingredients, new sources. And sometimes people come to us and say, okay, I have this slurry, I have this mass. It has is high in protein, is good protein, but we don't have a structure or we don't have a texture. And then I think the extruder can always add value or add texture quality to a product because I mean I'm not an expert in cell meat or in precision fermentation, but what I understand is at the end you have the protein but maybe not the steak. And if we want to make the final product with the same product characteristics, we may add another structuring process or step, which could be extrusion.
Yeah, I would be really interested in the conversation at the intersection of almost upstream
Yeah.
texturization methods and downstream texturization methods, because within the cell cultured meat space or the cultivated meat space, we see a lot of the texturization discourse around scaffolding, coming up with the right biomaterials, of
Hmm.
which the cells themselves can seed and grow into more three-dimensional structures. And yeah, I am really interested in how the downstream processing, like extrusion methods, might complement that production process. Any thoughts on that
Me
before we
too.
go over to our next question?
I fully agree to you. Yeah, it would be interesting. Yeah.
Awesome. Asking more about high moisture extrusion in terms of shelf life with and without freezing. Can you comment on the shelf life of high moisture extrusion extrudates um, before and after the freezing process?
So, I mean, in the extruder, we have the high temperatures. So, when it comes directly out of it, it is a very clean product from a microbiological perspective. But as soon as it exits the extruded die, microbes come from the outside and maybe from the marinade stick to the product. And as it is a warm product when it comes out, and it has a high moisture content, so it can quickly start to spoil. So if we just put it without appropriate packaging into the fridge, then after a few days it might get spoiled. So there are other ways some companies are doing that. They uh, use pasteurization or a combination of MAP packaging. We have recently a study here with high pressure processing. We've seen we can extend of a fresh product the shelf life if we do high pressure processing and non-thermal technology to extend the shelf life. So there are ways, and freezing is probably not the only or not the golden way, but it's something to make your product safe. And yeah.
Thank you. Um, we have a couple questions here about the limitations of the extrusion process, both kind of acknowledging them and challenging the bounds of pre-existing limitations. One question is whether you can comment on um, like whether to produce whole cut products, you can incorporate two or more phases of different colors and compositions to form a more realistic muscle fat connective tissue structure with high moisture extrusion or any of the other technologies you mentioned.
Mhm. Yeah, that's also part of current research going on, and I think there are different approaches how to do that. Um, Working with colors is very interesting, and also with different phases. I mean, you can inject a fat, a separate fraction, but it's always a matter of how it is well distributed. So that is not that easy. We have other ways and approaches I may not talk about today, how to go a little bit around and to have also kind of the marbling effect. Then it's difficult to have everything in the extrusion process, but maybe to do it in a subsequent way to bring it together. And maybe there are others who already have some solutions, but I'm not aware of. So, yeah.
Awesome. Are there any limitations on what can be added during the extrusion process? You had talked about like adding some oils and proteins and water. Are there any limitations on what you definitely should not be adding into this process?
I mean, we worked also recently with yeah, natural colors and natural flavors, and if they are not heat stable enough, and you want to have a red color, then it may not work. So you need to find good ingredients, and ideally, you don't want to use the full artificial uh, arsenal of ingredients you could use. But if you want to do it on a natural way, it's a little bit more narrow to find the good ingredients. So when it comes to color and taste. And as a third point, yeah, juiciness is also important factor. You can add oil, but only to a certain extent. And yeah, so adding things, yeah, that there are maybe limitations with that perspective. Yeah.
So you did talk about kind of the quality of ingredients that you put into this process. Do you do any kinds of pre-treatments on those input plant proteins, and does that end up influencing the texture?
Oh, yeah, maybe one thing just comes to my mind is yeah, using blends of the plant proteins. Maybe not just saying, okay, 100% soy or 100% pea, because then I have also a little bit the issue of this taste. If I just have 100% fava bean, then it has really a beany flavor. But if I can mix it with others, maybe we can create some synergies to improve the functionality, and the taste and color. So we found it helpful to mix the ingredients. And what was the other part of the question? Sorry.
The other part of the question was basically whether you pre-treat any of these
Ah,
ingredients to influence
mhm.
downstream.
Pre-treatment sometimes relate, yeah, to blending ingredients or to add a little bit of water to make the flowing property of the powder to improve it. Sometimes it doesn't sound so tricky, but it can be to bring the raw materials into the extruder, because when they are very fine and dusty and have a poor flowability, that is sometimes the first challenge to bring them into the extruder, and that may require some pre-treatment.
Got it. Thank you. Two last questions here, and then we'll wrap up our seminar. One question is, what approaches have you taken to address the flavor, the kind of off flavor issues that you surface as, a major challenge?
Yeah, one thing, using blends of different protein sources, maybe also working with natural ingredients like onion powder or pepper, or because they have a or stronger taste, and they have a savory taste. So in some cases that matches, and of course, you can also look for maskers. Yeah, that also works. But in my opinion, it still has some flavor or some impression that doesn't taste so natural then. But that's maybe a personal
Gotcha.
impression. Yeah.
Yeah. So maybe I think across the board, it seems like off flavors and plant proteins are a pretty big challenge.
Mhm.
I know
Yeah.
our hope is to get more breeding efforts underway in the plant protein community, such that those off flavors are not quite
And,
as.
and and particularly, if I may add that, when we look for ingredients that are cheaper and less processed, then they have typically a higher beanie flavor if we work with the concentrate. So that is also a little bit
The
the
trade-off.
off trade. Do we want to go for the isolate that has a bland or flat um, taste, but then we have maybe higher ingredient costs and also higher footprint of the ingredient, or yeah. So that's, I think, the research needs to go.
Mhm. Absolutely. Thank you so much. Last question here. So would you say that these technologies, I guess high moisture extrusion in particular, is very widely available for commercial use? And if a small business were to try and adopt it to enter the alternative protein market, what are some of the key considerations you would recommend that this business keep in mind in terms of finances and other relevant aspects, if they were kind of try and take this approach?
Mhm. I mean, that is a little bit the service or the gap we also as an institute want to fill, particularly for startups and maybe for companies who doesn't have the biggest investment and can afford in all this technology by own um, resources. So this is, we would like to consult them, to support them making the first steps in the space, and if they like the collaboration, we can move on together. We can produce. We did, yeah, for also products that are a little bit more exotic or have different ingredients, and there is no big producer who's doing that, then we say, okay, yeah, we can do that, or we can try to help you at least. Yeah, and that is a platform we're offering. Yeah, and when the money is there, yeah, then building own equipment, of course, is good or nice, but not always possible for everyone.
Mhm. Makes a lot of sense. There are big startup costs, absolutely, to
Mhm.
having these types of facilities. All right. Well, thank you so much again, Dr. Volker Lammers, for this presentation. It's been a joy to have you with us today. Thank you to everyone in the audience from all around the globe for taking the time out of your days to attend and learn from Volker. And we hope you all have a fantastic rest of your day. Very much looking forward to seeing you all at our next Science About Protein seminar. Thanks so
Yeah,
much.
thank you very much, Amy, and everyone for joining.
Bye. Thank you.